Hi everyone. So I hope you enjoyed your weekend. This is the lecture that will be for 2-17, but I'm out of town, so this is just a lecture recording. So to start, I wanted to remind you of some of the derivative laws that Catherine covered on Friday. So you saw derivations of the following derivative rules. And I think we saw this notation in class on Friday, but just in case it hasn't been explained before, you can write d divided by dx, and that just means take the derivative of whatever follows in the parentheses. So this was the constant rule. If you take the derivative of any constant, you get 0. Okay, so that's what that's saying. We have a constant multiple rule, which says d by dx of a constant times some function in x is the same thing as the constant times the derivative of that function, which we just write often as f prime of x. Then we also saw the power rule. And this is equal to n times x to the n minus 1. And we only proved this for positive whole numbers n, but it in fact works for any number. So for example, if I wanted to put in 1/2 here, this rule would still work. So you would get 1/2 x to the 1/2 minus 1, which is minus 1/2, just as an example. So you can use this rule with any number n. We also saw the sum rule. So d by dx of a sum of two functions is just equal to, you take the derivative of each function and add them. And same thing for our difference rule. So I'll just write here, if I instead were subtracting these functions, you would get that. Okay, now the situation for a product of functions is not as nice. So it doesn't work the same way where you just take the derivative of each function separately and then multiply them. It's a little bit more complicated. So here is what you get. So for the product rule, if I take d by dx of some f of x times g of x, then what I get is f of x times g prime of x plus g of x f prime of x. Okay, so that's the product rule. And then we also saw the quotient rule, said d by dx of f of x divided by g of x. And this one's a little bit tricky to remember. So you can derive it actually using the product rule together with thinking of dividing by g of x as a -1 exponent and applying the power rule. So here's how that works. So we're gonna get, so let's think about this in the following way. So d by dx of f of x times g of x to the -1. You know what? I just realized that we need something else that we haven't learned yet called the chain rule. So scratch this, hold this thought. We will use this in like 1 or 2 days to rederive the quotient rule. but there's one more ingredient that we need to in order to do that. So for now, I'll just write the formula. So we get g of x times f prime of x minus f of x g prime of x divided by g of x squared. Okay, so on Friday, we saw all of these derivative rules, and you can use these in combination with one another now to take the derivative of many different types of functions. So polynomial functions, rational functions, etc. So today what we're going to do is learn how to take the derivative of the sort of elementary trigonometric functions. And so you can add those into the list of functions that you're able to take the derivative of. So the first question that we're going to look at today is, how do you take the derivative of sine x? Okay, so that's what we're going to focus on for the first part of the lecture. And this calculation is a little bit involved in some places, and we're going to need some new ideas in order to finish this calculation. So we'll focus on that for the first part of the lecture, and then once we've done that, we will move into some examples of calculating derivatives of functions that involve trig functions. So what is the derivative of sine x? So let me just draw a graph. Oops. Let me draw a graph on the left of sine x. Okay, so it looks something like this. It's 0, and then 1, and then 0, and then minus 1, and so on. Okay, so it looks something like that. And on the right, I can plot what the derivative looks like. And we'll just do this using the idea that the derivative should be telling us what the slope of a tangent line is at any given point. So at x equals 0, it looks like the slope of this line is 1. So I'll just record that here. It looks like 1 there. Here, it looks like it's 0. So we get a 0 there. And then here, it looks like it's minus 1. And then looks like as you go further out, it's 0 again. So, and yeah, again, here on the, over here going this way, it's 0. There, sorry, 0. And then maybe minus 1 over here. So like a minus 1 there. So if we just connect up these dots, okay, so this is not very precise, but just sort of naively, we're just plotting a few points and linking them up. It sort of looks like this is going to be cosine of x. Okay, so that's our guess, just based on plotting how the picture looks, that we might get cosine of x. Okay, so let's actually compute it. So we'll just go straight from the definition. So we know that if I take the derivative of sine x, so we're just going to use our definitions. This is going to be the limit as h approaches 0 of sine x plus h minus sine x divided by h. Okay, so then what we're going to do for this calculation is first, I'm going to use the sign of sum formula to break this up. Okay, so we get the limit as h approaches 0. So we have sine of x cosine of h plus cosine of x sine of h. And then we have that minus sine x term. And then we're dividing all of this by h. Okay, so then the next step of this is that I'm going to collect together the terms that have a multiple of sine x. So that would be this term and this term. Okay, the middle term does not have a copy of sine x in it. And I'm just going to break this up a little bit. So we get limit as h approaches 0. So we have that sine x cosine h minus sine x divided by h. And then we're adding, so for now this is all in one limit, cosine x sine h divided by h. Okay, so now since both of these terms have a sine x, I can pull that out. So I'll just factor it. So we get the limit as h approaches 0 of sine x times cosine h minus 1 divided by h, plus this other part, cosine x sine h divided by h. Okay, so now I can break this up using the limit laws. So we know that the limit of the sum of two things is just the sum of the limits. Okay, so that's one thing. But then we also have a constant multiple rule for limits that tells me that I can just pull any constants out front. And if you think about it, the limit involves the variable h. So that means that this, from the point of view of h, is just a constant. So I can pull this out of the limit. Okay, so this is going to just break up into the limit as h approaches, oops, sorry. I'm going to do two things simultaneously. So I'm going to pull out sine x, and then I have the limit as h approaches 0 of this other stuff, cosine h minus 1 divided by h. Okay, and then I also have a second limit. So I'm going to use the sum law for limits. So I'm going to have another limit over here. And for this one, cosine of x is the constant. This doesn't involve h, so I can pull that out. So I get plus cosine x limit as h approaches 0 sine h over h. Okay, so this step was simultaneously, this was by sum and constant multiple limit laws. Okay, so now that we have this, we have these two limits. These are not continuous when h is equal to 0, so we can't just plug in h equals 0. And it turns out that they're actually a little bit tricky to evaluate. So this one on the right, this is actually equal to 1, and we're going to prove that, okay? The one on the left, this is equal to 0, and it's done in the book using this limit. So basically, in summary, how do you find this limit? You do some trigonometric trickery to just rewrite this expression. And then when it comes down to it, all you need to know is actually this limit on the right. So if you're interested to see how that works, the calculation is done in the book. And we're just going to calculate this one on the right. But once you do those two, so for now we'll just assume that these are true. So once you do that, since this is 0, all of this will go away. And then since this is 1, we are just left with cosine x. Okay, so that's what we wanted to show. So this tells us that the derivative of sine x is cosine x up to, I owe you the calculation of that limit on the right. Okay, so let's do that limit. So we will evaluate and I'm now going to think of the argument of sine, so the variable, as an angle. So I'm going to put in theta for the variable. So we're going to take the limit as theta approaches 0 of sine theta over theta. The theta doesn't really matter. It's just reminding me that I'm thinking of this as an angle, which is going to be helpful for the geometric arguments that we're about to make. So let me give you an overview of the idea of how to do this. So basically what we're going to do is we're going to show that cosine of theta is less than sine theta divided by theta, which is less than 1. So we will argue both of these inequalities using some geometric reasoning. And then how does this give us the final answer? So we show this inequality, and since the limit as theta approaches 0 of cosine theta is equal to 1, right? Because cosine is a continuous function, so we can just plug in, and cosine of 0 is 1. And this is also equal to the limit as theta approaches 0 of 1. Of course, that's equal to 1. So since these two limits agree, right, as theta goes to 0, so this inequality is going to be satisfied for all values of theta, and as theta goes to 0, these two things become 1. So that means that this will also be forced to be equal to 1. And this is a fact that's called the squeeze theorem. So I'll just say, since this is true, by the squeeze theorem, which we haven't stated yet, I'll state it in a second, we have that the limit as theta approaches 0 of sine theta divided by theta is equal to 1, which is what we wanted to show. Okay, so let me state the squeeze theorem. So what does this say? So this says, let's suppose that we have some element A in some interval. So where I is an interval. If we have a series of inequalities, so we know that g of x is less than or equal to f of x is less than or equal to h of x for x's coming from the interval, and we know that the limit as x approaches a of g of x is equal to the limit as x approaches a of h of x. If these are equal, so they agree and they equal some number L, then f is also forced to have that limit. Okay, so that's what the squeeze theorem is telling us. So let me draw a picture of how this is looking. So let's draw Let's say g is some pink function. Let's say it looks like that. And let's say h is some green function. Let's make it like, I don't know, something like that. And then if f of x, say this is blue, is really anything in between these, so maybe it's some wacky thing, it's like bouncing around a lot, whatever f is doing, the limit, in this case, a is 0, is forced to be the same value as the limits of g and h by the squeeze theorem. Okay, so let's zoom out. We wanted to show, let's zoom all the way out. So we wanted to show that the derivative of sine x was cosine x. It boils down to the fact that this limit is equal to 1. So we wanted to calculate that limit. And we showed that this is equal to 1 as long as this inequality is true, right? Because this inequality forces the limit to be 1 by the squeeze theorem. So we need to prove this inequality. So let me just copy this. Okay, so we need to show so we have two things to show. One is the left inequality and the other one is the right inequality. And I'll just do them side by side here. Okay, so I actually find the right one to be a little bit easier to understand. So let's start with that one. Okay, so for this, we actually need to remember the definition of sine theta and draw a unit circle type of thing. So I'm going to rearrange this. So this inequality is true if and only if sine theta is less than 1. Okay, and this is something we know to be true because if I draw any angle theta, right, the height, so this is like inside of a unit circle, this height is the value of sine theta. And that is at most 1 because that is the radius of this circle, right? So we have that sine theta. Oh, sorry, I need to, sorry. Of course, I meant to multiply by theta. So we need to show that sine theta is less than theta, which is a little bit trickier. Okay, so forget about what I just said. So, okay, so here's our unit circle. This height is sine theta. And let's think about what theta is in this picture. Theta, by definition, is the length of this arc. Maybe I should do this in a different color. So this is this red arc. So theta is the length of this arc. Okay, but of course, the length of that arc is going to be longer than the height of this line segment. Okay, so that's why we get that sine theta is less than theta. Okay, now for the other inequality. So I'm also going to rearrange this one. So this inequality is true if and only if the inequality theta less than sine theta over cosine theta holds. And of course, sine theta over cosine theta is equal to tan theta. Okay, so what we want to show is that theta is less than tan theta. Okay, so here's the picture for this. So I'm again going to draw some angle theta. and this arc here. Okay, so what is tan theta? Tan theta is equal to the slope. Let me move this a little bit. Tan theta is equal to the slope of this line. Okay, so if I extend this line out to x equals 1, which is here, this is x equals 1, this point lies at 1 comma tan theta. Okay, because tan theta is the slope of that line. Slope is rise over run. So if run is equal to 1, then the change in y is equal to the slope, which is tan theta. So that's the coordinates of that point. And then, like we said before, theta is equal to this arc length. This is theta. So what we want to argue is that this arc length is less than the length of this line. Okay, so let me label a few things. So let's call this point B, this point A. This point is going to be, the pink point is D. And then I'm also going to drop a perpendicular here and get E, that point there. Okay, so theta is equal to the arc from A to B. So I'll just call that arc AB, the length of that arc. And hopefully you find it believable that this is strictly less than the length AE plus the length EB. So maybe I'll make an argument why. Okay, so we're saying that this arc has shorter length than those two segments. And the reason is, you can imagine if this was a whole circle, that was a very bad circle. But anyways, if this is a whole circle, then BE is creating for us a polygon that circumscribes the circle. Okay, and the perimeter of that polygon is going to be larger than the perimeter of the circle. And this is just some small portion of that. Okay, so that's why we get this inequality. And then we can also see that EB is shorter in length than ED, because ED is the hypotenuse of a right triangle involving a leg EB. So I can replace this. So again, this is less than, I'm leaving AE alone. And EB becomes ED. Okay, but AE plus ED is exactly this vertical line. Oops, let me get the laser pointer. It's this vertical line, which has length tan theta. Okay, so in summary, that proves this inequality here. We also have this inequality. So this all holds, and then by the squeeze theorem, this limit, the limit is this, as theta approaches 0 of this thing has to be equal to 1. Okay, so that was the calculation. So let's now switch gears from doing all these proofs and do some examples. So let's do an example here. Let's take the derivative of x squared times sine of x. Okay, so the key with these derivative problems is that you need to see how to break up complicated functions into simple ones so that you can use the rules. So what I see here is a power function, which we know how to take the derivative of because of the power law, times the sine function, which we also know how to take the derivative of. So what I need to do, so this is the product of two functions that I know how to take the derivative of. So I need to use the product rule. Okay, so let's do this. So take d dx of x squared sine x. So step one, product rule. So here we'll do product rule. So what I need to do is take the derivative of one of them, multiply it by the other one, add it to take the derivative of the other one and add it to the first one. So we'll have d by dx of x squared times sine x plus d by dx sine x times x squared. Okay, so let's apply the power law to this. So what we do is we take this exponent down, bring it out front, and reduce it by 1. So we get 2x to the first, and that's times sine. Maybe to differentiate this from x prime, I'll just put a 1. Okay, so that's times sine x. And we're adding that to, we need to take the derivative of sine x, which we now know is cosine x, times x squared. Okay, and that's basically as simple as it gets. To simplify, I would really just remove that exponent on the x, because x to the 1 is just x. So this would be our final answer here. Okay, let me just tell you what the derivative of cosine x. So using similar methods to how we took the derivative of sine x, you can also find the derivative of cosine x, and it is the following. So d dx of cosine x is minus sine x. Okay, so this becomes a little bit tricky to remember because like sine x and cosine x almost are each other's derivatives up to this pesky minus sign. So just remember sine x, derivative is cosine x, derivative of cosine x minus sine x. So you pick up a minus sign. Okay, so using this, let's do another example, which is we'll take the derivative of tan x. So we'll take d by dx of tan x. Okay, so how might I do this? Well, I know that tan x can be rewritten as sine x over cosine x. Okay, and this is a quotient of two functions, each of which I know how to take the derivative of. So I'll apply the quotient rule. So we get, this will be by the quotient rule. Okay, so for quotient rule, it's kind of like product rule. You have to take the derivative of one, multiply it by the other one, and then do the same thing in reverse. And instead of adding them, you subtract them. So the order matters. And the one that you subtract is the one where you took the derivative of the denominator. That's how I remember it. Okay, and then you also divide by denominator squared. So let's do that before we forget. Okay, so we have cosine x. times derivative sine x minus sine x times derivative of cosine x. So another way that I sort of like try to remember this is bottom d top minus top d bottom all over bottom squared. Okay, so that is what we get from the quotient rule. Okay, so let's simplify this. We get cosine x, derivative of sine x is cosine x, minus sine x, derivative of cosine x is minus sine x, all over cosine squared x. Okay, let's simplify again. So now we get cosine squared x plus sine squared x all over cosine squared x. Okay, now your trigonometric spider senses should be tingling because you know what this is. This is just equal to 1 by the Pythagorean identity. So we get 1 over cosine squared x. This is by Pythagorean. Identity. And 1 over cosine squared x is the final answer, but people also write, this is, of course, 1 over cosine x is secant x, so people write secant squared x is the derivative of tan x. I was gonna do one more of these before writing down what all the formulas are. So let's do secant, and then I'll just summarize all of these in a table. Okay, so let's take d by dx of secant x. Okay, so what is secant x? This is, so d by dx of 1 over cosine x. And again, this is all about seeing how to break this thing up into functions that you know how to take the derivatives of. So what I see here is a quotient of a constant and a cosine, both of which I know how to take the derivative of. So I'm going to use the quotient rule here to break this up. Okay, so bottom d top, so cosine x times derivative of top, which is 1, minus top d bottom, so 1 times d dx cosine x all over bottom squared. Okay, so let's simplify. So d by dx of 1 is 0. So here we just get 0 minus, well, this is going to be, so derivative of cosine is minus sine. Don't forget the minus there. This is minus sin of x. So this all together is plus sine x, because these two minus signs, sign, cancel each other. Okay, 0 plus sine x all over cosine squared x. Okay, so then this is more or less the final answer, but people again rewrite it. So if I pull out one copy of sine x cosine x, that gives me tangent x. And then I'm left with 1 over cosine, which is secant x. So this is how the derivative of secant x is usually written. Okay, so let's write down all the formulas for these trigonometric functions. Okay, so we have d by dx sine x is cosine x. D by dx cosine x is sine x. D by dx of tan x is secant squared x. Writing these down almost feels like writing down like a conjugation table in a language class. I think it's just because of the way that I laid this out. But d by dx of cosecant x, which we didn't do, but you could, if you wanted to, just like the previous example, calculate this using the quotient rule, and you get minus cosecant x times cotangent x. Okay, and then d by dx of secant x. We just calculated, this was secant tangent. And then lastly, we have cotangent, which you could also calculate using the quotient rule. And this is minus cosecant squared x. Okay, so let's finish up with one last example. So we're going to find the 27th derivative of cosine x. So here's how this looks. I'll write it. All right, d by dx to the 27 cosine x. Okay, so here's how it goes. And let's just make, I'm gonna actually do this on a new page. I'm gonna make a table. So I'm gonna put n for what derivative we're taking, and then what the nth derivative is. Of cosine x. Okay, so the first derivative of cosine x is minus sine x. The second derivative, okay, so the minus sign we can just pull out because this is just multiplying sine x by a constant -1. So then we're just looking at the derivative of sine x, which is cosine x. So we get minus cosine x. Okay, 3. Now we're taking the derivative of cosine x and multiplying that by -1. So derivative of cosine x is minus sine x times -1. So we just get sine x. 4. Now derivative of sine x is cosine x. And then if we wanted to take the fifth derivative, so I'm back where I started, right? I was originally taking derivatives of cosine x. I found that the fourth derivative of cosine x is equal to cosine x. So if I want to continue taking derivatives, let's say I wanted to look at what the fifth derivative was, well then I'd just be starting back at here again and moving through the table. So the fifth derivative of cosine x is just going to be minus sine x. This agrees with the first derivative. So what we get is that at multiples of 4, so when n is a multiple of 4, we get that the nth derivative of cosine x is still just equal to cosine x. So what that means is that I can just go, if I want to find the 27th derivative, I need to find the smallest multiple of 4, or sorry, the largest multiple of 4 that's still less than 27. So this is going to be 24. So we'll look at the 24th derivative. That's going to be cosine x, right? Because 24 is 6 times 4. Then 25, 26, and 27 will just be given to me by these, right? So 25 will be sine x minus sine x. 26 will be the next one, which is minus cosine x. And then 27 will be the next one, which is sine x. And now we're done. So the 27th derivative of cosine x is equal to sine x. Okay, so that's everything that I have for you today. So we'll stop there and I'll see you in class on Wednesday.